Welcome, my dear students. This new class. In the last class, we discussed about the eigenvalues, some eigenvectors, and eigenspace, and we have some equivalent conditions about the eigenvalues and eigenvectors. This section we discuss about some example, some special types of a matrix. If we have a diagonal matrix, if we have a upper triangular matrix, if we have a lower triangular matrix, symmetric matrix, and symmetric matrix, singular matrix, what a different type of matrix, how can we find the eigenvalues and eigenvectors for the different types of a value matrices there. Okay, let's begin with the first with the eigenvalues of an upper triangular matrices. So we can say that find the eigenvalues of an upper triangular matrix. So we just try to find the eigenvalues of this 4 by 4 upper triangular matrix. So this is a 4 by 4 upper triangular matrix. We just try to write into this form. We have to write again, we have to just say that we know that we have to write A of V is equal to lambda of a V, some vector into V is the lambda of a V. So we just write what in the form of this, or we can just last time we just said that we calculate the determinant of A minus lambda I is equal to 0. We have to find the characteristic equation. Characteristic equation is, you know that the characteristic equation of this is equal to A minus lambda I, and characteristic polynomial, this is characteristic equation, and this part is called as the characteristic polynomial. So we just take a determinant of this. We can calculate the determinant of this matrix. This is lambda 1. So we just corresponding to this we can calculate into this form. So this can be written in the form of a lambda minus A11, and then we have a matrix like this. We have a determinant we going to this way. So we have this is lambda minus A22, a minus ka A23, and so on, minus ka A24. And then we have a 0, then we have a lambda time minus ka A33, and then you have a minus ka A34, and then we have a 0, then we have a lambda minus A44. Now next step, we just take right into this form. So we just write, this can be written in the form of this, or okay, just we try to this. So lambda minus A11, and then we have a, now corresponding to this, so you have a lambda minus A22, and then we calculate this. Again we have to matrix like this, lambda minus A33 minus ka A34, and then you have a 0, then you have a lambda minus A44, and this can be written the completely, we can write lambda minus A11, then lambda minus A22, then lambda minus A33, and then we have a lambda minus A44. So if we have any matrix which is in the upper triangular matrix, then the eigenvalues is nothing but is equal to, you say this is the only the diagonal vectors of a this. We can say that clearly. This means we can say that, you can see here we have a diagonal value of this is the only the eigenvalues of this string. So that means clearly if we have a given matrix in the form of a either triangular matrix, means upper triangular, or the lower triangular matrix, always there is a diagonal elements are the eigenvalues of this thing. So this means is equal to this. Now we have this is a trivial solution. Unit determinant is equal to 0. So this means we can say that put this is equal to characteristic equation in the form of this lambda minus A11 and lambda minus A22, and this. And then this is equal to 0, means product is 0, this is equal to 0, this is equal to 0, this is equal to 0. So this means lambda is equal to A11, lambda is equal to A22, and lambda is equal to A33, and lambda is equal to A44 are the precisely diagonal entries of A, and these are the eigenvalues of any triangular matrix. Okay, so now just the following example should be evident the computation in the preceding example. I just take this theorem is saying that if A is an n by n triangular matrix, upper triangular, lower triangular, or the diagonal, then the eigenvalues of A are the entries of the main diagonals of A. That means we can simply say that the eigenvalues of a matrix where is A is a triangular matrix, maybe is a upper triangular, lower triangular, or diagonal matrix, then the eigenvalues of such a matrix is the entries of a diagonals are the eigenvalues of this. For example, we take this, we try to find by the method of this, we have a determinant of a minus lambda I, but according to the theorem we can say that by the, because this is a lower triangular matrix, so if the lower triangular matrix means we have a this diagonal elements of this is, you have a this, so you have a, these are the only eigen values of this, so this means we can say that lambda 1 is equal to, you have a 1 by 2, lambda 2 is equal to, you have a 2 by 3, lambda 3 is equal to minus 1 by 4 by the previous theorem. Or if you want to, we can just check if this is equal to, we take a determinant of a minus lambda I, and then we can take a determinant of a minus lambda I or lambda I minus a, both are the same. So we just take a this equation can be written in the form of a determinant of this matrix A is equal to 1 by 2 minus lambda, then 0 0, then you have a minus 1, 2 by 3 minus lambda, then 0, then you have a this is, you have a 5, and then you have a minus 8, then you have a minus 1 by 4 minus lambda. Now this can be written as a, you have a 1 by 2 minus lambda, and then we have to just go into this way. So this is, now we have a 2 by 3 a minus lambda, and 0 minus 8 minus 1 by 4 minus lambda, and then we can say that calculate into 1 by 2 minus lambda, or you have a 2 by 3 minus lambda and minus ka 1 by 4 minus lambda, and that is equal to, characteristic equation is equal to 0. So we can say that lambda is equal to half, we can say that lambda is equal to 2 by 3, and lambda is equal to, we can say that we have a minus ka 1 by 4. So this means clearly we can say that if we have a diagonal matrix, then there is no need of a calculating this method, just directly use the this theorem. We say that if we have any triangular matrix, that the diagonal elements are always the eigenvalues of the given matrix. Okay, so this just already calculated. So this means this is equal to 0. So lambda is equal to, we have a, this is equal to 2 by 3. Sorry, this is, you have a 2 by 3. Not lambda is equal to 2 by 3, and then we getting the solution of this thing. Okay, now we have a point to be noted. If A is a triangular matrix, either lower triangular, upper triangular, or the diagonal, then the eigenvalues of A are the diagonal entries. Just we have to show that. If A is a symmetric matrix with the real elements, then the eigenvalues of A are always real. That is a very important property. If we have A is a symmetric matrix with real entries, then the eigenvalues of A are always real. Now, if we have A is a non-symmetric matrix, then the eigenvalues are either real or a complex conjugate pairs. So this means if we have a symmetric matrix with real element, then eigenvalues of A is always real. If A is a non-symmetric matrix, then its eigenvalues are either real or the conjugate. So we have to already discuss this by the example. Now I try to explain by these two also example. By first we take a symmetric matrix. Now we have this is a symmetric matrix. Now we can find the determinant of a minus lambda I. So this is a minus lambda I. You can just say that 1 minus lambda and 1, and then we can say that 1 and 2 minus lambda. Then we can calculating this is equal to 1 minus lambda, and then you have a 2 minus lambda, and then you have a minus 1, and this should be equal to 0. So we can take this is equal to trivial solution, and the determinant is equal to 0. So non-trivial solution. Then we have to simplify this. You can see this is simplifying this. You have a we can just say that is equal to 2 minus lambda, and then you have a minus ka 2 lambda and plus ka lambda square and minus 1. So you have a lambda square minus ka 3 lambda, and then you have a plus ka 1 is equal to 0. Then you can say that lambda square we have a we can just take a minus ka 2 lambda minus lambda, and this can be we calculate into a this is the equation is this. Now we can calculate the lambda is equal to, you have a this is roots the quadratic, then can say that minus b plus minus b plus minus root of b square minus ka 4ac over twice a. So this means you have a we have a minus b, so this is equal to, you have a 3 plus minus root of b square, you have a 9, and then you have a minus ka 4, and then over 2a is equal to this, so 3 plus minus root 9 is equal to, you have a 9 minus 4 is equal to 5 by 2, so this is equal to 3 plus root 5, 3 by 2 root 5 by 2, and we have another is a lambda 1 is equal to this, and lambda 2 is equal to, you have a 3 by 2 minus root 5 by 2. So this means we can say that this means we have a getting the equation is this, lambda 1 is equal to 3 by 2 1 by 2 root 5, then 3 by 2 minus 1 by 2 root 5. So this means these are the all are the real. So if we have a symmetric matrix and entries are the real, then we can say that clearly this matrix is always is a, we can get always is a real, eigenvalues are always real. Suppose we have to take the characteristic equation. If this we just take a lambda minus a plus by 2, this is equal to 3, and then we just take a in the form of a this eigensymmetric case. Now I just take a if we have a non-symmetric matrix, if we have a is equal to, we have a 1 minus 1 1 and 1 minus 1 1, so we can just say that we can take a determinant of this is equal to 1 minus we take a determinant of this matrix, we can write in the form of a 1 minus lambda and 1, then minus 1 2 minus lambda, and then we can calculate is equal to, you have a 1 minus lambda and 2 minus lambda and minus minus plus 1, this is equal to 0, and this is the equation. This means we can say this is into this form, and now you simplify this, you getting into this form. Now you just take you have a, you can take into this form into, you have a b square minus 4ac, so you have a 3 plus minus root b square is equal to 9 minus 4ac, 4 3 is a 12 over, you have a 2. This can be written as a 3 plus minus root of minus ka 3, and then we can say that this is nothing but is equal to upon root 2. Then you can say that root of minus 1 is equal to, you know that I, so this can be written as a 3 plus minus I and root 3 by 2. So this means lambda 1 is equal to, you have a 3 by 2 plus I times of a root 3 by 2, and then lambda 2 is equal to, you have a this thing, and lambda 1 is equal to, you have a this thing. So if we have to change this equation into a non-symmetric eigenvalues, because according to this thing, if A is a non-symmetric matrix, then its eigenvalues either real or complex conjugate pairs. So this means we can say that this matrix we have to taking is a symmetric matrix. This is the same matrix we have to taking, because 2 minus 1 in this case I just change here. In this another matrix we have to just change is the form of a 1 minus 1 and this. So this means this is clearly is as a non-symmetric matrix. And if the non-symmetric matrix, then the eigenvalues of this are lambda 1 is equal to 3 by 2 upon this, and then this is a pair for real and the complex pairs in this form. So this way we can calculate this thing, a non-symmetric matrix, and then we have to just take a diagonal matrix. For example, if we have a diagonal matrix, then we can say that if by the theorem we can say that this is the diagonal element are the its eigenvalues. So this means lambda 1 is equal to 1 and lambda 2 is equal to 2 are the eigenvalues of this diagonal matrix. So this means I just calculating in this form because the theorem is already, so we can no need of a calculating here, but I try to calculate this, but there is a no need of a calculating eigenvalues of this. We have to just say that the eigenvalues of this simply is equal to the diagonal entries of this matrix is the eigenvalues of this. So means lambda 1 is equal to 1 and lambda 2 is equal to 2 are the eigenvalues of this thing. Okay, now we have to try to find the this vector, and this is we have to try, this is the lower triangular matrix, and then you know that the eigenvalues of this clearly this is equal to this 2 according to the by the theorem, and then clearly lambda 1 is equal to 1 and lambda 2 is equal to 2. Now we try to find the what is the basis, or you can say that eigenvector of this. So we have to take a corresponding lambda 1. We write the equation of this. We can say that if we have to write lambda is equal to 1, so we just write in the form of this lambda minus 1 x plus we have to write is equal to y, and then is equal to you have a 0, then you have a simplify into this, you have a 0 plus lambda minus 2 into y is equal to 0, like this. So we just say that take any vector x is equal to x1 x2, then this product is equal to 0. So we can say that lambda is equal to, if we take a 1, then this is equal to 0. So 0 0, then you have a is equal to 0. This means you have x1 is equal to 0, and you have a you have x2 is equal to 0, then x1 is not arbitrary. So by this system equation we getting only for a you have a x1 is equal to 0, and then x2 is equal to, you have getting the 0. So x2 is equal to 0, that means we can say that v lambda is nothing but is equal to, you have a in the form of a t times you have a 0 t in the form of any arbitrary x1 is equal to for the moment of a t. So we can say that this is equal to t and 0, and such that t is the any real number. Then we can say that this can be written as a t times of a, we have a 1 0, and such that t is the element of a r, and this can be written as a span of, we have a 1 and 0, and this eigenvector of this is if for a t is any arbitrary vector. So we can say that this eigenvector of this is equal to 1 and 0. So this is from 1 t1 to this. Now for lambda is equal to 2, we just substitute here lambda is equal to 2 minus 1 is equal to, you have a 1, and you have a 2 minus 2, you have a lambda is equal to 2. So this is again you have a something we can write this in the form of a this into x is equal to 2 times of a x1 x2. So this gives a system equation, this is equal to x1 plus 2 x1, or we can just solve this is also in this form. Substitute here is lambda is equal to 2, so 2 is 1 2 minus 1 is equal to 1 and 1, so you have a 1 1, and so this we have to getting 1 1 0 0, and then you have a x1 x2 is equal to 0 0. Then you can say that clearly you have x plus x1 plus x2 is equal to 0. Then you have a x1 is equal to, you have a x1 is equal to, you have a this is 2x1, x2 is equal to x2. So this means we can say that this can be written as x1 minus x2 is equal to 0. So this means we can say that clearly this is, you have a 2 minus 1 and 2 minus 2 is equal to 0. So this means x1 is equal to x2. So this means we can say that there is again is a infinitely many solution. So this lambda is equal to 2, then can be written as a, this is x1 plus x2 is equal to 2 times of x1. Then you have a twice x2 is equal to twice x2. So we have to here just take into this form. So we can just write into this form is equal to, you have a we can write in the form of this x2 is equal to, you have a twice x1 minus x1. So this is equal to twice x1 minus x1 is equal to x1. So x2 is equal to, you have x1. So x2 and x1 are the same for arbitrary. Then x1 is equal to t comma t. T should be not equal to 0 eigenvector of a corresponding to the eigen values of a lambda is equal to 2 is there. So this means we can just say that we have a matrix here. This is equal to. So we can say clearly we have a this if we take a 2, so this means 1 1 0 1, and then okay, this is clear. And now if we have another matrix, we try to find we take a 1 minus lambda 1 1 and 2 minus lambda, then this will be is equal to, we can say that you have a 1 minus lambda and you have a 2 minus lambda, and then you have a minus 1, this should be equal to 0. Then clearly we can say that this can be written as a, you have a lambda square, then minus 2 lambda and minus 3 lambda, and then you have a 2 minus 1 2 minus 1 is equal to plus 1 is equal to 0. Then you can say that lambda can be written in the form of a 3 plus minus root 9 minus 1 9 minus 1 upon 2. So this is equal to, you can write 3 plus minus root of 8 over 2. So root of 8 means we can write is equal to 3 plus minus 2 root 2. 4 2s are 8, then it is equal to 2. So this can be written as a 3 by 2 plus minus root 2. These are the eigenvalues of this. We can say that clearly. That is equal to, we have a clearly minus 1, and then we have to substitute here. So this simplify this, you can clearly what is this, you have a lambda square minus ka 3 lambda minus ka 3 lambda, and minus minus you have a minus and minus 2 plus 2 minus 1 is equal to 0. So lambda square minus 3 lambda plus 1 is equal to 0. So this means lambda is equal to, you can say that is equal to 3 plus minus root of 9 minus ka 4 upon 2, then it can be written as a 3 plus minus root of 5 upon 2. So this means we can lambda 1 is equal to 3 1 by 2 5, and this is equal to 3 minus 1 by 2 5. Then we can find the base characteristic equation eigenvalue for this. Corresponding to this, we can write this into this x1 and x2. So this means we can say that similarly x1 plus x2 is equal to 3 by 2 plus 1 by 2 root 5 x1, and then you have a x1 plus twice x2 is equal to 3 by 2 plus 1 by 2 root 5, you have a x2. So just we can write this is equal to x1 plus x2 is equal to this, x1 plus 2x2 is equal to this. We have to simplify this. Then we can say that simplify this, you can just x2 from here, you can just x2 can be written as a 3 by 2 plus 1 by 2 root 5 x1 minus ka x1. This can be written as a 3 by 2 minus ka 1 and plus ka 1 by 2 root 5 of x1, and this is equal to, you have a 3 minus 1, so 1 by 2 plus 1 by 2 root 5 of x1. This can be written as a, you have a 1 by 2 times 1 plus root 5 x1. So this means this can be written 1 by 2 x2 can be written to this form. Similar fashion, x1 can be written in the form, x1 can be written in the form of a this form. This x1 can be written in the form of a, here by the second equation we can write 3 by 2 minus ka 2 and plus 1 by 2 root 5, and then this is equal to x2. So this is equal to, you can write 4, so you have a minus half and plus half root 5 x2. So this x1 is written in the form of this by these two. So just we can write from first one. So x1 can be substitute x1 and x2 in here. So we have to just substitute here. Just we can get x1 is equal to this into x2. So this one into this is equal to this is we can x1. So this x2 value substitute here. X2 is equal to, you have a this value. Then we have to is equal into this is x1, and then we can say that this into this x1 is equal to, you have a getting x1. We fix x2 is equal to, you have a t from b then we get x1 is equal to this into t. So therefore we have the x1 is equal to this and x2 is equal to, we have a t. And now these two equations are the same because these two equations are exactly the same, x1 and x2 are the same. We can starting from x1 and x2 is equal to x1. So these are the we getting, if you take x1 is equal to, you have a this into x2 is equal to this into x2 is equal to, you have a this into x1, and if you have to multiply these two equations, you get 1 by minus 1 by 4 plus 1 by 4, and then you can just cancel out, you can getting only the 1 minus 1 by 4 or 5 by 4, and then clearly minus 1 by 4 and 5 by 4 is equal to, you have a 1, and then clearly x1 is equal to this one. So this means we can say these two equations are the exactly the same equation, a and b. So this means we can x2, if x2 is equal to t, then x1 is equal to this t. So this means this is the t is not equal to 0 eigenvector of a corresponding to the eigenvalue of lambda 1 is equal to 3 by 2 plus 1 by 2 root 5. Similarly, if we take a lambda 2 is equal to this form, then we have to multiply it into this again, and then we can get x1 is equal to this, x2 is equal to this. Again, these two are the same. If you can just take x1, you can just take a x2 from here. So x2 can be written as a 3 by 2, and then you have a minus 1, and minus 1 by 2 root 5, and then you have a 3 by 2 minus 1 by 2, so 1 by 2 minus 1 by 2 root 5 of x1, x2, and then these two equation again giving the same values. So we just taking from here. If we take x1 is equal to some t s, so then this x2 is equal to this form. So x1 is equal to this, x2 is equal to x2 is equal to this, x1 is equal to this. So both are these are the same. So we can say that take x2 is equal to x1 is equal to, we have to getting the some value for s. Then x2 is equal to, we getting this value. So x2 is this into s. Therefore s is not equal to 0. So we can, according to the lambda 2, the eigen vector corresponding to the lambda 2 for eigenvalues in this form, s into this, and this means you have a s is any arbitrary, and then we can just complete the solution of this problem. Okay, one more problem we try for the 3 by 3 and find the eigenvalues and eigenvector for this corresponding matrices. So we start with the this matrix. So just say that we have to starting from this right in the form determinant of this form. So the characteristic equation of this mean we can write is equal to 0 minus lambda, 0 minus 2, 1, 2 minus lambda, and then we have a 1, then we have a 1, we have a 0, and you have a 3 minus lambda. Now we just take into this form. We have to starting from the suppose which corresponding to this form, we can just take a, so we can just write in the form of a 2 minus lambda, and then we have a this goes to, and this goes to, you have a 0 minus lambda minus 2 and 1 of 3 minus lambda, rest of them zeros. We can say that 2 minus lambda, and you have a minus lambda into 3 minus lambda and minus 2 and then plus 2, and this is equal to 0. So this means we can say that clearly one of the lambda is equal to 2 is one of the roots. So then this is equal to 0 means lambda is equal to 2, and also we can simplify this. We getting is equal to lambda square minus ka 3 lambda plus 2, and then is equal to, we can say that lambda square minus ka 2 lambda plus ka, sorry, minus lambda plus 2 is equal to 0. So this can be written as a lambda times of a lambda minus 2 minus 1 times lambda minus 2 is equal to 0. So this lambda minus 2 and lambda minus 1. So this means the roots are is lambda minus 2 ka whole square and lambda minus 1. So this means this equation has, and the roots are, this equation is clearly lambda minus 1 and lambda minus 2 ka whole square. So this means there are the distinct eigenvalues of a lambda is equal to 1, lambda is equal to 2. There are the two eigenspaces for A. First corresponding to, we have a x is equal to this, so we have a matrix is equal to in this form. So we write into this form, substitute lambda is equal to 2 first. So we have a 2, and then we have a lambda minus 2 0, lambda minus 3 is equal to 1. So this is equal to, sorry, minus 1. So this is the value for this. Now we have to make this, either we have to using the elementary row operations. We have to just R3 can be replaced as a minus ka R3. So you have to, R2 replaced by minus ka R2. So you have a and replace this by the R1. So you just say 1 0 1, and then we have any this is 2 0 2 and minus 1 0 minus 1, and then we can just R2 replaced by R2 minus ka 2 times of R1, R3 replaced by R3 plus R1. So we have a 1 0 1, then 2 minus 2 0 0 minus 0, 2 minus 2 minus 2 is again 0, then you have a, this is 0, then you have a 0, and then this plus this is equal to 0. So this means we can say that clearly we getting the only equation is this x plus x1 plus x3 is equal to 0. So x1 is equal to, you have a minus x3. So if x3 is equal to, you have a s, x3 is equal to s, then x1 is equal to minus s, and x2 is another arbitrary vector because x2 is not involving here. So because we have only one system of equation and 3 variables, so we have two free variables are there. So three variables and one system of equation, at least we have a, so two are the free variables. So one is corresponding to the x2 is a free variables, and x2 and x3 are the same, minus 3. So this means x3 is equal to, we have s, then x1 is equal to minus s. So x2 is equal to, we have a 2. T, then the eigenvector corresponding to the lambda 2 is a non-zero vectors of the form of this. We can just say that x can be minus s t s, and this can be written as a minus s 0 s 0 s t, and then this can be written as, so these are the eigenvectors of this, and they are linearly independent. Clearly you can check, none of them is a scalar multiple of other. So these vectors form a basis of an eigenspace for lambda is equal to 2. So that means we can say that these two vectors are linearly independent, so they form a basis into the in this form. Okay, so now just for a corresponding to lambda is equal to 1, and now we have a this is equation is we have a this is lambda, so lambda is equal to 1 1, 1 minus 2 is equal to minus 1 and minus 2. So we have a just 1 minus 1 minus 2, and again using the same technique we have to just take a here just we have a 1 0 2 is the equation as Gauss elimination method, 1 0 2. Adding these two, you getting the 0, adding to this minus 1, adding these two is equal to, you have a 1, and then you have adding these two 0, then you have adding these two 0, then you have a minus 2 2 is equal to 0, and then clearly you have this equation, you have a x1 plus twice x3 is equal to 0, then you have a minus x2 plus x3 is equal to 0. So we can say that x1 is equal to minus twice x3, and x2 is equal to, we have a x3. So if x3 is equal to, we have to take a s, then x1 is equal to minus twice s, and x2 is equal to, you have a s, and then we can say that the eigenvector corresponding to the lambda is equal to 1 is equal to minus 2s ss. So s is equal to minus 2 2. So this is the non-zero vector, and this is clearly is a linearly independent. And if this is linearly independent, then we can, this is a form a basis. So this means we can say that this is a form a basis for this. So this complete the solution of this problem also. So now we just say that this complete this problem of this eigenvector, and then whatever this now very interesting thing, I just say that whatever eigenvector we have to calculating, and eigenvector we have to calculate, they form a linearly independent set, and if they are linearly independent set, they form a basis. So I just stop today class here, and in the next class we continue about the this discussion. We starting from this, we have to write this eigenvector. So we have to show that this all the, if we have all the distinct eigenvector corresponding to the all the distinct eigenvalues corresponding to the eigenvectors are always linearly independent. So we discuss all this some properties of a eigenvalues and eigenvector into the next class. So up to this is thank you very much for this.